In this video, I want to talk about hypothesis testing. And we've done a lot of kind of nitty-gritty stuff with hypothesis testing, and if you've forgotten some of it, I would urge you to go back and watch earlier videos on kind of the specific tests. But I just wanted to do kind of a broad overall picture here and talk about things that you would want to look for. So in each one of these, let me just explain my table. Like, how do you know which test to use? What's the state portion? What are the plan? What are the conditions? And the do. What test is it? What do you return? And just overall, I want to talk about those three parts of your conclusion. So in a t-test, what do you look for a t-test? Well, obviously, you look for a sample mean. Okay, that is true of these two as well. In a t-test, you look for a deviation. Okay, a sample deviation. I'm going to write that. And you look, in this case, for one sample size. Okay, so that's a 1N. That's what that stands for. And here, you end up with two of them, right? You have two samples, in which case you should have two deviations and two sample means. Now, the matched pair is the hardest one to kind of pick out of this, because oftentimes you are given two sets of data, and you condense it down to one. So we look for, really, is there an important reason to pair data together? Okay, and that's something that's sometimes hard to pick out. It's obvious when it's like a before and after situation. You say, well, it's, the person before the diet and after the diet. That's easy. Other times it's harder. Let's say you're comparing heights of fathers and sons. That's important to pair a father and son together. You can't compare one boy to a different father. So you have to look for, is it important that I pair this data together and then boil it down to a difference? And that's the other thing. You end up with just one mean and one deviation, and those are for the difference. I'm going to write this. I'm sorry, it's getting a little messy. The difference. So this two sample t, this is the only time you have two x bars and two sample deviations. Okay? Proportions. What do we look for? Well, we look for a proportion, or we look for a, x out of n. Like, oh, we had 15 out of 500, something like that. In two, we have two proportions. We have basically two samples, two n's. Okay? In a chi-square test, the first thing that you could look for both chi-squares is more than two categories. Okay? More than two categories. The minute you start talking about putting things in 3 or 4 or 5, it's no longer a proportion test. It's on to chi-square. That's for both. For goodness of fit, basically you look for a one set of expected value, or one set of observed values. And in an independence test, you look for a table of observed values. Basically, you've broken into categories in two directions, right? That you have, you're saying, well, I broke it down by not only their class in school, freshman, sophomore, junior, senior, but then I also broke it down by their income level or something like that. You've broken into categories in two directions and almost made a table of it. And linear regression is probably the easiest to spot, because obviously you're talking about the slope, right? You're looking for a pretty specific type of test here. All right, so now the state. In every single state, this is where you do your null and your alternative, okay? And I'm going to write down kind of the nulls. So we have a mu equals blank, the population mean, and we have a number. And remember, you have to define your mu. You say mu is the population mean and put it in context. Okay? Now, with two samples, the null, is mu1 equals mu2. And I'm not going to write the alternative. Obviously, it's a different inequality. It's greater than, less than, not equal to. Same thing is true here. It would be, mu is not equal to, greater than, less than. That same number. Use the same number in both spots. Here you can use subscripts. You could say like the average 20-year-old is equal to the average 30-year-old. You can use subscripts to define your variables if there are two samples. So going on to the matched pair, remember that the matched pair, the null, because we've condensed it down to one list, is the mu is equal to 0, that there was no difference. And again, your alternative would just be, greater than, less than, not equal to. A one proportion test. So the null is that P is equal to blank, and for a two proportion, P1 equals P2. And again, same rules apply here as the T in terms of, first of all, make sure you're using a parameter to state your null and alternative. It should be the same values in both, same numbers, right? And if you only had one sample, define that parameter. What does P stand for? It's a population proportion. And if you have two, you can use subscripts. The proportion of men equals the proportion of women, or something like that. Okay, you can use the subscript. So again, make sure you're writing this correctly. Make sure you are using parameters. Make sure you're keeping the numbers the same if it was a one sample. Okay. Now the goodness of fit. This is remember we have the observed is equal to the expected. And we have this, kind of a fill in the blank piece like that. It's the observed distribution of scores is equal to the expected distribution of scores. The observed distribution of ice cream cone types is equal to the expected distribution of ice cream cone. So we really observed distribution equals expected. Now the chi-square test for independence, the null, oh, I'm sorry, I didn't write a null here. The null is really that the two variables are independent. Okay, so that, you put some context to that, but that's the null. That your class is independent of your gender. Your GPA is independent of your attendance. Something like that. Okay, and for linear regression, the null, remember this is where we have that beta. The slope is 0. And again, we have to define that. The beta is the population slope between, X and Y. All right. Now, during the plan portion, everything needs to be a simple random sample. We want good data for everything. Okay. For the t-test, and for all of the other tests, we have that 1/10. Sample size is 1/10 the population size. Okay? Remember here, we want samples that are 30 or larger for these three. For proportion, we use that NP is bigger than 10, N times 1 minus P is bigger than 10. Okay? For chi-square goodness of fit, we use that expected count is bigger than or equal to 5 for both of these. Remember, you should be writing those down. If it's a chi-square test, you should write down those expected counts. For goodness of fit, you might have to calculate them. For independence, remember, it would be put into a matrix and you could recopy it down. Okay. For the two samples, we need the samples to be independent. I'm going to add that here. Independent samples. And again, that goes for the two proportion test as well. It obviously doesn't go for chi-square because they are dependent on one another. The last one, kind of the different condition here for linear regression, you remember it's liner is the way we write it. And that stands for Is the data linear? Were they independent samples? Is the distribution of residuals normal? Is the standard deviation equal? And was there randomly collected data? Okay, so again, linear trend, independent samples, normal distribution of residuals, equal deviations throughout the linear approximating, and finally, was it random? It's at this portion in the plan where it's always also nice to name the test. To actually write down, these are the tests I'm using. To write t-test, two-sample. And I'm just going to make a note of that. It is nice at that point to name the test. Okay, the do portion of this is all done with the calculator. Tell what the test statistic is. So for t, of course, it's a t. So remember your degrees of freedom. Remember, you could do that as a subscript for those two. For a proportion test, it's a z. Here it's a chi-square, and remember again, degrees of freedom. And here it's a t, so remember degrees of freedom. Now remember here for these t statistics, the t is the degrees of freedom is sample size minus 1, and for linear regression it's sample size minus 2. Okay, so remember, report your test statistic, and if degrees of freedom are necessary, the only time it's not is the proportion test. And then give your p-value. Okay, so the do should have two pieces to it. Finally, the conclusion is 3 parts. Okay, for all of these, it's 3 parts. First part. Okay, first part. Say what you're doing with the null. Are you rejecting or failing to reject? Okay, tell what you're doing with your null hypothesis. That's number 1. Second piece, tell why in terms of the p-value. Why are you doing that? It's because the p-value is smaller than the significance level, so your p-value is less than 0.05, reject. Or are you failing to reject because the p-value is bigger than the tell why. And the third is, what does that mean in context of the problem? We have evidence that the mean is higher than it used to be, or that the two proportions aren't the same. Okay, so use that we have evidence, or say we don't have evidence. We have insufficient evidence. Okay. So again, you may want to look back at some of these kind of individually, but this was an overall idea of all the different types of hypothesis tests. Be very careful in your work. These are typically not that hard on the AP exam, but they do require some, being exact with your null and your alternative and the way you show your work.